Okay, let's go ahead and get started. I'm going to talk about a concept that I've been working on for some time, which is using composite materials to actually suppress mode suppression in microstrip edge coupled features. And this is actually kind of a neat trick, I think. But to begin with, let me go through some of the basic ideas. First off, all microstrip edge-coupled features that are half wavelength related have this spurious mode type of thing. And what I mean by that is you have a center frequency, and then the spurious mode, or the mode that you do not want, can occur at even multiples beyond that. So f sub 0 would be the center frequency, and 2 times f sub 0 would be the mode that would be spurious or not well, or that's not what the designer wants anyway. And it also can happen at 4, f sub 0, 6, but basically even modes. And so these spurious modes are problematic really for a filter because the stop band is then not well defined, as you'll see. And also there's several different ways that you can minimize these spurious modes. And most of the ways that I've looked at are pretty complicated actually. So they've got different type of designs that the resonators, instead of being rectangular here, they're kind of a sawtooth. In some cases they have capacitors they add to it to actually change the length, electrical length, and they do a lot of different tricks, but most of those tricks are somewhat they complicate either the design or the printed circuit board fabrication or the assembly. And really the ideas that I'm showing today is going to be a simpler version of that to minimize these spurious modes. So the way these spurious modes behave is really due to phase velocity of the different modes of the filter or the edge coupled feature. So edge coupled features have an even mode and an odd mode as shown here. And in even mode, you can see that the electric fields used by the wave propagating on the medium are mostly using the z-axis or thickness axis of the material itself. So the dielectric is what the electric fields are using. And in odd mode, you have the same thing where the dielectric is being used by the electric fields, but there's also some coupling between the adjacent signal conductors. And in that coupling area, there's error that's being used, and error obviously is a lower dielectric constant. So what happens is the odd mode effective dielectric constant is lower than the even mode effective dielectric constant. And because of that, the odd mode actually has a little faster phase velocity than the even mode. And faster is not necessarily good, it's just different. So when you have different phase velocity in even mode and odd mode, that's what causes these spurious modes to happen. And it can be very problematic for filters and couplers or anything that's edge coupled like that. And then the other thing I should also explain is the term effective dielectric constant. That term is basically saying that's the dielectric constant as the wave would perceive it on the transmission medium. So what I mean by that is the wave has electric fields that's using substrate and also electric fields that's using air. The combination of air and substrate, that's the effective dielectric constant as the wave would perceive it. So the idea here is really to use a material, composite material basically, that's using two different types of materials. One has a low dielectric constant, one has a higher dielectric constant, and different thicknesses. And there's kind of a magic ratio, as we'll see as we go through here, of thickness and dielectric constant that can help these modes to become equal for phase velocity. So in the case of even mode, well actually let me back up a second. In this case, the upper left, or the upper drawing that is shown here is a 2 copper layer circuit. So it's a microstrip edge coupled. And you can see that I have two different materials in there, a high dielectric constant material and a low dielectric constant material. The high dielectric constant material is basically a laminate. And what I've done was etch off one layer of copper off a copper clad laminate, and then I use a low dielectric constant bonding material to bond another copper layer to it. And that's how I've got the 2 copper layer circuit. So what's interesting here is I'm really adjusting the even mode because the even mode is using the z-axis or thickness axis dielectric constant almost exclusively. And the odd mode is actually using the same thing, but the odd mode's actually got this coupling here where it's using some of the air and some of the substrate. But the addition of this lower dielectric constant material at the base there is not really affecting the coupling. It's really affecting the z-axis or thickness axis only. So really what's going on here is I'm adjusting the even mode effective dielectric constant more so than the odd, and lowering the even mode, so it's going to be closer matched to the odd mode. So I've looked at a lot of different combination of materials, different thicknesses, different dielectric constants, things like that. And really this slide is showing a summary of the different things I've settled on for this particular design. And in this case, what I'm looking at is a material that's used a lot in filters and couplers, and that's the RT Doroid 6010.2 material. And it's got roughly a 10.2 dielectric constant when tested per IPC test methods that we use. And then another material I'm using is a bonding material, which is 2929, and that's got a dielectric constant about 2.9 when tested in the same IPC clamp strip line test method. And the combination of these two materials were used, and what I did was I used Sonnet software, which is an electromagnetic modeling software, and the software is able to give me what the effective dielectric constant is for even mode and odd mode both. And using that software and a simple relationship is given here for phase velocity, what I did was look at different relationships of the 25 mil RT Doroid 6010.2 material compared to different thicknesses of the bonding material, the 2929. And as you can see on the table here, well, to begin with, let me take a look at this standard material, the couplers basically using the 6010.2 material only. And you can see that, yes, the effective dielectric constant is higher in even mode, lower in odd mode, and the phase velocity is going to be faster in odd mode. And that all makes sense. And what I've decided for this study is actually use ID number 3. And the reason why is ID number 3 is using 6 mil thick 2929, and you can also see that's got the least amount of difference between the different modes for phase velocity. The other thing is, in the reality of making a circuit, if you start off with a 6 mil thick 2929 bonding material, actually going through the lamination process, you're going to end up a little bit less than 6 mils thick. And it could be 5.9, could be 5.5. It depends a lot on the geometry that this material is trying to fill. So if you start off with a 6 mil bonding material, and you can see that's already in a good range for matching the even and odd mode phase velocities. And if it does go down in thickness, which it will, it's either going to be 6 mils or less, basically, from a nominal point of view. Then if it does go down, it's going to go down to be 5.5 or something a little bit less than 6. And as long as it stays between the 5 and 6, that's right around the range you want. You want to have zero difference between the phase velocities. So 6 mil as the nominal seemed to be a pretty good choice. So these are some models I've done here in Sonnet software. And from a design point of view, what I did was use a Chebyshev transfer function, 0.1 dB maximum ripple, and also low-pass prototype synthesis technique, which is used very often in filter design anymore, and it's really defined by Matthew and Jones many, many years ago. But I have that reference if anyone's interested in it. So what I did was I designed a filter at 2.5 gigahertz as the center frequency, which means it's going to have a spurious mode that we're not going to like, about 5 gigahertz roughly. And then the other thing I did was look at different designs where it's the exact same design, same center frequency, but different bandwidth. And the reason I did different bandwidth is because to get different bandwidth, you need different coupling. And this method is sensitive to coupling. So in the case of the design where I have a 180 megahertz bandwidth, that's actually loosely coupled. So the distance between the edge-coupled conductors is actually spread apart a little bit. In the case of the 440 megahertz bandwidth design, that's more tightly coupled. So the signal conductors are much closer together. And in this particular type of technique, the coupling is pretty critical to understand the difference in phase velocity. So what I did was these models, and you can see that the center frequency is roughly 2.5 gigahertz, and then you do have a spurious mode on the standard materials using just 6010 material only. And it's got a pretty bad response actually, where it's up about 6 dB or 8 dB or so. And in the case of the composite material with the same design, it actually has a response there too as well, but it's hard to tell at this scale. That's actually a really good response. That's about 40 dB. So the difference from 8 dB down to 40 dB, that's actually a very good cleaning of the spurious mode. And then the wider bandwidth, the 440 megahertz bandwidth, same idea. It's with just the standard materials. It's not a composite. You get about 8 dB or so in the 2F naught range, and then with the composite material, it goes down to about 40, which again is actually really good. It's kind of hard to tell with this scale. And then I had circuits made and tested them, and this is the results from the circuits being tested. And the circuits with 180 megahertz bandwidth is on the left, and the yellow trace is really the standard materials used in the 6010 materials. And you can see that you've got the 2F naught that's really pretty significant there. And in the case of the blue curve, which is circuits used in the composite material, that is much more quiet in that area. In fact, actually the stop band looks really good for that filter. So that particular filter has 180 megahertz bandwidth in the passband region, and then once you get away from that, you should have a good stop band that's pretty far down in the S21 curve. And in the case of the blue curve, which again is the composite material, it's actually pretty well behaved. So this trick really did work quite well for minimizing this second spurious mode. And then the other example would be the same concept, except now looking at 440 megahertz bandpass filter, same center frequency, about 2.5 gigahertz, and you got a spurious mode using the standard materials, about 5 gigahertz. And you can see what happens when you use materials with the composite design, that it goes down a heck of a lot. And it's around about 45 worst case, and outside of that, it's much better. So it really does make a significant difference on quieting that second order harmonic, which again can be really important for filters and radio systems. So that's all I have on this topic. I'd like to leave with talking about our technology support hub. And this is on our website. It's something we're pretty proud of. We have a lot of good information here. We have microwave impedance calculators that you can be run from the web page itself, or you can actually download it for one that has more capabilities. Also have some videos that are generally pretty short videos, 5 minutes, 7 minutes long, of topics that are just an introduction to topic and a lot of different topics. Then we have papers that we give at white shows, copies, or white papers that we give at trade shows, something like this. And we also have the ability to contact one of our tech support people through Contact an Engineer. So if you would like, we'd like to introduce you and ask you to be a member of our Technology Support Hub, where there's a lot of valuable information there, I believe. Okay, no questions? I guess I'm done. Thank you very much.